everyone. So today we are going to present our senior project, which is focused on characterizing fracture toughness of 3D printed nylon 12 for medical applications. I'm Ruchi.
I'm Shreet.
So let's get started with our presentation. So focusing on the outline, we'll start our presentation with the background of 3D printing, and then we would like to move on to explain you all about how we expanded our senior project from last semester's project. And then we would move on to understand the motivation of our project and the gap in market, why we chose to do this project, moving on to the literature review, and then diving into methods and results of our project, and then we would like to conclude our presentations with future work and acknowledgements. So moving on to the background of our project, so background of 3D printing was, initially 3D printing was used for prototyping 10 years back, but eventually down the line it was used to manufacture and produce different kinds of materials, including medical devices. So why 3D printing came into the market and played an important role, because it was cost effective and the production line became more efficient. So 3D printing was one of the main techniques used into the industry, and our project used a very advanced 3D printer, which is HP Multijet Fusion 3D printer, which was released in 2016. So we printed all our samples using this printer. Moving on, as we discussed that we did our senior project based on the previous year. So previous year focused only on two tensile properties like yield stress and tensile stress, but we wanted to go into much more detail and explore the fracture toughness of the medical devices, because that is the most important aspect while building them. Also, we included different parameters like print bed location, print orientation, and print settings, which we will be discussing in a bit. So as you can see from this image, the previous project used the tensile bone, which is a dog bone, according to a different standard, and we produced CT specimen. So that is one of the main important aspects which we changed in our project. Moving on to understanding fracture toughness. So what is fracture toughness? Fracture toughness is ability to resist brittle fracture when a crack is present or when a deformity is present into the samples. So why fracture toughness is important while building medical devices? Because it is completely avoidable while processing and fabrication, and it is a very important aspect while building medical devices, because the medical device should be able to withstand different kinds of stresses and strain while it is in the body or on the body. So that is why fracture toughness is important to consider while building medical devices. So what is our motivation to dive deep into understanding fracture toughness of polymers like nylon 12? So recently nylon 12 is being used to develop 3D printed arm casts and AFO, which is ankle foot orthosis. So while building these so ankle foot orthosis is used to for a patient to heal their bones. So because a patient wears this while conducting their daily activities like walking and running, so the AFO cast needs to withstand lots of stresses and strains. So it should be built in a certain manner or in a certain orientation, and that is why it is important to consider the factors we are considering, which is print bed location and orientation, and also print speed, because print speeds matter and can influence fracture toughness of the material printed. So from this image you can see that figure A is the arm cast, where it is a non-bearing implant, and the fracture toughness does not play an important role for this device, but it does play an important role in AFO cast. So we will move on and explain you more in detail in other slides. So FDA considerations. So we can use our project in building class 1 devices like the arm cast, like we discussed before. So the 3D printed arm cast would help the bones heal faster, are more comfortable and waterproof, and they are the larger movements towards 3D printed medical devices. So building personalized devices for patients would be more beneficial, because it would be more cost effective and it would be more comfortable for patients to wear in future. So literature review. So this is one of the papers from which we use the data and came to know our expected results. So as we came to know that ZXY orientation produced highest fracture toughness, moving on with XYZ producing the lower one, and the lowest fracture toughness was produced by XYZ orientation. So that's what we will be considering. We considered in our project these kinds of orientations while printing our samples using the 3D printer. So what we're trying to solve here. So there, in the current market and in the current literature and the research, while you go online and research, you wouldn't find much data based on 3D printed nylon 12, especially printed from HP Millijet Fusion 3D printer. So there is a minimal data available on polymers right now, and especially no fracture toughness data for HP Millijet Fusion 3D printed polymers. So, and fracture toughness is not widely studied right now by scientists and researchers. So we wanted to lay a groundwork and gather data for future work.
So I'll be talking about the design of experiments. So for our input factors, we have 3 parameters that we're considering: print bed location, print sample orientation, print speed, and the 4th number is print number. It's the different printers that we're using for our project. And the different numbers of levels for them are: print orientation has 3 different orientations, XZY, XYZ, ZXY. Print bed location is the location where the specimens are built, and that's just ordered as left, right, and center. And print setting, there are 2 settings that I'll be using for our project, for all of our specimens, and those are mechanical and balanced. And in total, we'll be printing 72 samples for our project that will account for all the parameters that I just listed. Design of our specimen is based on ASTM standards, and especially E399 and D5045 were used to design the specimen in SolidWorks, and then that's what was used to print all our specimens. This is just a schematic representation of our specimen, which is just a block with a pre-manufactured crack in it, and the 2 holes will be used by the instron to pull apart and induce the crack propagation. And these are this is a diagram for the print orientation. These are the orientations for ZXY, XYZ, and XZY. And these are the locations. So this is the print bed, and left, center, right. That's how the specimens are going to be built. And the mechanical imbalance is just that mechanical is a faster print, so the mechanical properties of balanced is going to be better than mechanical, and that's a known fact. But we're still using these settings just to see if how fracture toughness compares for these 2. And methods for printing specimens. So since our project is not a big project for our Jabil, we had to think of a way to print our samples in a faster scale so as to take less time for producing all of our specimens. So we decided to print our samples to do 4 print jobs with 2 layers. So each layer is of 9 samples, so each print job has 18 samples. 9 on the bottom layer, which is called A, and the top layer, which is B, and this is from printer 1. And from printer 2, we'll be doing layer C and D. Same thing, C is the bottom layer and D is the top layer. And so in total, from the 2 printers that we'll be using, we'll get 72 samples. Another thing that I left out was that all our samples are labeled so that we can identify them. And there are 2 labels on both top and bottom end so that we can identify the samples once they're fractured and also before. And so the methods for, once we get our samples from the Jabil manufacturing team, we'll be sandblasting them. This is so that the powder, the nylon 12 powder that is inherently on top of the specimens can be removed, so our specimens are clean before we start doing any experimentation. Once we have the specimens cleaned using sandblast, we will measure the thickness, width, and weight of each specimen, just to keep track of the dimensional consistency of all our specimens before we induce crack propagation. And this is a schematic of how the crack propagated one of our samples, which we'll talk about more. And testing specimens. So we decided to test our specimens in by layers. So we decided to do a layer A of mechanical and layer A of balanced, and that was set 1. Similarly, we decided to do set 2 then after layer A with layer C and layer C both balanced and mechanical. So what we were thinking was to do a set of 9 samples from mechanical and 9 from balanced from one layer. So even if we do something wrong or if we find, we should have done something differently, we still have another set that we can use to repeat our test. And methods, so Instron was basically our sole device that we use to do our testing. Basically, it's just a device that pulls apart the specimens, and there's a software with it that records our fracture toughness data, and that's what we use to do our calculations, which we'll talk about. And these are the equations. All these equations are found in the ASTM standard that we talked about earlier. And pretty much once we get the data from the Instron software, Blue Hill software, we will just calculate these values, and eventually the KQ is the fracture toughness constant, and that's what we will finally we'll get a number to represent for each specimen's fracture toughness, and we will just organize them according to all the parameters like print orientation, print bed location, and the specimen type, and mechanical setting or balance set.
So after all the 72 samples were fractured using Instron, and we gathered all the data using Blue Hill software, we generated various graphs and calculated all the KQ values as Shreet talked about in the last slide. So we generated bar charts for each orientation. So this is for printer GU1, the first printer, and the mechanical print setting. So as you can see, ALZXY produced highest fracture toughness for layer A, and for layer B, again, it's PLZXY, which is 3.883. So it complies by the literature paper which we went through before conducting our tests. So ZXY had the highest fracture toughness, so that orientation produces higher fracture toughness due to how it's layered. It's layered diagonally, and all the other orientations like XYZ and XZY are layered parallelly. So it was more difficult for the crack to propagate for ZXY orientation rather than other orientations. And the blank line you see here is just because we fractured the sample on our own and not by mistakenly while putting it up on the Instron, by setting it up on the Instron, and not using the actual Instron software. So it was a mishap while conducting our experiments. So we also conducted visual inspections, which Shreet will talk about in detail in the later slides. But as you can see, I'm comparing the two specimens which produced highest fracture toughness out of all the 72 samples. So ALZXY had the least thermal bleeding. What is thermal bleeding is basically how much heat is applied to the sample while they're printed on the print bed. So as you can see, this represents the lightest color, which means it has the least thermal bleeding. And there was a small indentation on the top of the specimen, and we did not observe this blue color represents no, which means we did not observe any elephant skin, which is the rough skin which we find on the surface of our specimen. And as you can see, the crack type is curved up, so it's curving up. So that's how we defined all our 72 samples by conducting visual inspections. Whereas we saw a more amount of thermal bleeding for BLZXY compared to ALZXY. And as you can see, it's a 3 crack type, so it's curved down. And again, we saw no elephant skin for the mechanical layers A and B. So same way we conducted, we produced bar charts for mechanical print settings and for printer 2. And for here we found out that CR XYZ produced highest fracture toughness, and DL XYZ produced higher fracture toughness for D layer. So you can see how the mechanical print setting between printer 1 and printer 2 changes. So we found out that printer 1 was better than printer 2 due to some technical issues or technical problems with the parts of the printer. So we found that printer 1 was better than printer 2. Moving on with the results for C and D layer, you can see it's the same way, like thermal bleeding is less compared for the C layer to the D layer, because C layer was the top layer and it was exposed directly to the printhead, but D layer was the layer laid down on the print bed, so it had more thermal bleeding compared to the C layer. And this is for another print setting, which is balanced. So for balanced, we again found out that ZXY produced highest fracture toughness for both A and B layers. So this confirms our results more and more that we are going on the right track, and it complies again with the literature review which we studied before conducting our experiments, that ZXY produces highest fracture toughness. And again, this is the same inspection we conducted for balanced samples. So we found out that thermal bleeding and indentation was minimal on the layer A compared to the layer B. So the top layers had less deformities and less indentation compared to the layer in the down part. And again, this is for C and D layers. So each print setting had 4 layers. So this graph represents for C and D layer. Again, we found out that CLZXY and DRZXY produced the highest fracture toughness. And this is again the representation for our visual inspection. And we found more deformities in the down layer than compared to the upper layer. So moving on with the visual inspection.
So this is just how we were recording the visual inspection data for thermal bleeding, indentation. So what we basically did for each of these qualitative characterization, thermal bleeding, elephant skin crack type, is that we chose a color and we had different shades of it to represent how much of that was there present. For example, indentation, was it there? Yes, no. Linear curve, what kind of curve it is, and this way it's visually easier for us to track down patterns between mechanical, balanced, and also between the printers. And this is just the same thing for printer 2.
So after we conducted all the data and we calculated all the KQ values, we also did non-destructive analysis using 2 key instruments, which is SEM scanning electron microscopy and CT X-ray machine. So let's get started with SEM analysis. So this represents data for XZY and this represents data for ZXY. So ZXY orientation underwent brittle fracture. That means it has larger plastic deformation and it's more difficult for crack to propagate. Whereas XZY underwent, so this one underwent ductile fracture, this underwent brittle fracture, which represents that the specimen fractured quite quickly within few seconds, which means that orientation is not appropriate for building casts, arm casts and AFO casts. So the crazing here in the filaments, to conclude our SEM analysis, ZXY produced ductile fracture, which means it has higher fracture toughness, which confirms that, and XZY produced brittle fracture, which means that it's not suitable for medical devices and it produced lower fracture toughness values. And then CT scanning. So you can relate to this analysis with the SEM analysis. So ZXY had just 2 voids, as you can see here. So which confirms that it underwent ductile fracture. So 2 voids and ductile fracture correlates with each other because it has less voids, that's why it underwent ductile fracture, which means it took longer time for crack propagation. And XZY had 7 voids before fracture. So after fracture, it underwent brittle fracture. That means more voids, it is more easier for crack to propagate. So these 2 data we collected, which we could correlate with the quantitative and qualitative analysis.
And these are just schematics representing how we estimated the cost for all the equipment that we used, and also the labor costs for all the teammates that were working on this project, and also cost analysis for all the consumable products that we used. So in conclusion, printer 1 and printer 2, in both the printers, balance was better in mechanical as expected. And in both printers, a ZXY orientation had the highest fracture toughness. In the mechanical printer, there was no particular orientation. I had a consistent pattern of higher fracture toughness. So samples printed in ZXY and XYZ direction contain half or more of their filaments in the direction. That was orthogonal with the crack plane. So that's why we think maybe there was a significant obstacle to crack propagation. And the XZY did not have any filaments or inside the part that was printed aligned orthogonally to the crack plane. So that's why it had low fracture toughness. So future work would be obviously to repeat the study with the largest sample set, so we can see if our results are reproducible and repeatable. And also another thing that will be incorporated in future studies would be to induce a pre-crack with the razor blade as opposed to just a manufactured pre-crack. And additionally, randomize the print of samples. So instead of knowing, the experimenters will be blinded to the where the samples are printed. So it will be randomized set of samples. So statistically, we can be more sure of how the samples are, and that would help determine better fracture toughness data. So we would like to thank all of our Jabil staff, Quinn, Rosa, Noel, Jennifer, who's our advisor, Ian, and Peter Fraga, and the manufacturing team. And we'd also like to thank our SJSU professors, Dr. Keles, who is our advisor on this project, and Dr. Erogbogbo, who is our professor for senior project, and Dr. Solidere, our department chair. And these are our references. Thank you.
Thank you so much.